start recording. Okay. Thank you very much. Well, so this is the as we discussed last class, what are the relation between the mechanical angle and the electrical angle. If you take, for example, this very simple structure here, you have 4 poles. So if you have any conductor here, if the rotor rotates for 1 complete cycle, we have here 2, if this is 4 pole, under north pole, for example, it gives you the maximum. Under south pole, it will give you the minimum. So for this north pole, it will give a maximum and the minimum. So in this case, you will complete here 2 cycles, and it's 720 degrees. However, the mechanical angle here is only 360. And as we mentioned, this is the relation between the mechanical angle and the electrical angle. You consider here number of pair of poles, or B/2. Number of pair of poles or number of poles over 2. So this is the angle. If you take the derivative with respect to the previous equation, so you will get second derivative d theta square equal to dt d square delta as well. And equation of motion becomes you can replace d square theta m by d square delta m over dt square, and we will still continue modifying this equation in order to replace this mechanical angle to electrical angle. So you can of course convert from the torque to power, and power equal to omega t, power in general equal to omega t. So if you multiply both sides here by omega, so this is times omega, and omega times t equal to B mechanical and B electrical here. So it's better to have it in terms of power. لأن power is يعني you can measure it, so you can calculate it easily rather than torque. So this is the first step. J omega m, the angular momentum of the rotor. Sometimes we call it m. So you can define m as J omega m. If the inertia constant of the machine, then approximately you can write the equation as such. M, which is J omega, d square d theta m over dt square equal to the acceleration power. Assume machine rotor speed doesn't vary greatly from the synchronous speed. And this assumption is very valid. In real time, you can see the frequency is changing in very narrow range. Frequency maybe between 59, in regular cases, of course, 49.5 to 60.5. So omega equal to 2 by f. So the range of the frequency, the range of the speed is very narrow. You can have it if you multiply this by 2 pi or this by 2 pi, you will see the range of omega. The omega is almost constant. So it doesn't vary greatly from the synchronous speed. And to account for frictional torques, if we have frictional torques or some kind of losses between B mechanical and B electrical, eddy current, friction, windage, and all these losses, type of losses, we can consider the losses here in this term. So B mechanical minus B electrical minus, like a dashpot control system where you have a friction here, and it's proportional to the speed. So this could be the if you consider the frictional and eddy current losses, in this case you can add this term, which is proportional to the speed. Okay, so let us define here For this formula, M is J omega, is defined as J omega. This M actually is quite different from one machine to another. And some machines are small machines. You have, for example, 80 megawatt machine. You have 150 megawatt machine. You may have 625 megawatt machine. You may have 800 megawatt machine. So this J here is quite different from each other. So we have wide range of M. M is very varying very much with respect to the machine itself. So we can avoid this by having M as a per unit. So if we express it in per unit, so in this case, we will have some kind of narrow range of the inertia. So H is defined as, we define here H, which is the inertia constant, is the stored kinetic energy at the synchronous speed over the generator rating. So we relate the inertia now by, or kinetic energy, which is 1/2, kinetic energy is 1/2 J omega square. So we relate it to the, the rating of the machine. So we do some kind of, per unit quantities. So in this case, we have H equal to 1/2 M, طبعا J omega, you can replace J omega by M. So SM over S machine, and this is equal to stored kinetic energy. It is energy. You have it in joule, and this one in watt. So this H has a dimension of what? Dimension unit is second, and H is 5 seconds of a machine. If we have big machines, so you can have H equal to 10 seconds or more of this. But H here is, the range of H is very narrow compared to M. So in power system literature, we prefer to use H rather than M in the swing equation. So H is called H constant, or the inertia constant. The unit of H is second. H is preferred over M because H values fall within a fairly narrow range, while M value vary widely with the size or type of the machine. So we can go back to the swing equation and replace. We can divide both sides over S, and then you can replace this M and replace it by H. So we have in this form, we can replace M in terms of H. So yes, here it is.
Excuse me, Doctor.
Yes, please.
Yes, I have a question concerning renewable energy sources.
Go ahead, please.
Can this wind turbine generator, can it contribute to the inertia of the system, since it is not considered as a conventional generator? Or
wind?
Yes, wind turbine generator. Can it contribute to the inertia?
The wind generator?
Yes.
No.
Okay.
It doesn't contribute if you have, this is wind generator. If you have here conversion or power electronic converters, and this should be, you have it here some from AC to DC, and then DC to AC, in order to connect this to the grid. right?
Yes.
Such converter here, this will kill the inertia of the wind generator. So the wind generator doesn't contribute to the inertia of the system. And this is one of the major challenges in high penetration of renewable energy. And it doesn't contribute to the inertia. So if you look at this swing equation, you have here this swing equation, you have it here. Okay, so you can write this swing equation as let me continue this in order to have the final form of the swing equation, and then I will go back to this point. Okay, Sulaiman?
Yes, doctor, it's clear. Yeah.
So we replace M here by H, and then it becomes to this form. It's quite easy to find the M equal to H times S times 2 over omega. So 2H over omega, and this S will come to the other side. It will be B acceleration of S machine, and you divide this by S machine. So in this case, if you divide B mechanical over S machine, and now the power can be expressed embryonic. B electrical over S machine, power electrical embryonic, and this also embryonic. So we have 2H, H in second, over omega, V square delta by dt square, over the B equal to B mechanical minus B electrical embryonic. So we still have here mechanical angle and mechanical speed. So can we replace them by electrical angle and electrical speed? Yes, we can. We know that delta M equal to delta E over what?
PP. Feedball.
So here is delta is in numerator, and we have also omega in denominator. When you replace this by delta E, electrical angle, and this is electrical speed, so this pair of pole will go together. And this is the numerator and this is in denominator. So we can easily replace delta E, we can replace it by delta E, and we can replace this by omega S, synchronous speed, which is related to 2 by F directly. Okay, so we can do this. We can replace delta M and omega M by electrical angle and electrical speed. Okay, so this is number of variables, B over 2 in terms of electrical angles. Then this is the final form of the swing equation, where we have here delta is the rotor angle or power angle. So delta can be considered as a power angle or rotor angle. And this omega S synchronous speed is 2 by F. Okay. And these powers are embryonic. This is embryonic. And H in second. Okay. طبعا delta here in radian. And omega S is in radian per second. This is the speed. And delta in radian. Okay. So this is the final form of the swing equation, and delta the electrical degrees, omega S is in radian per second. Okay, that's fine. Now, if you look at this, and even in the initial format of the swing equation, when we say J equal to J times D square, then all D omega by dt, or D square theta, or D omega by dt, no problem. equal to T mechanical minus T electrical. You can write this as d omega by dt equal to B mechanical or T mechanical minus B electrical over the inertia J. So in this case, if you connect BV or wind, if you connect BV or wind, definitely you replace, and here you replace conventional generators. If you have BV plant or wind farm, and you generate 400 megawatt or 1,001 gigawatt, you have to shut down the conventional generator of, then you have load, and you need to supply the load, and load is fixed. You supply it whether from the conventional generator or from the distributed generation. But you have to supply the load. So if you replace some of the conventional generators by BV and wind, and the BV and the wind doesn't contribute to the inertia here. So this inertia becomes lower and lower. As the penetration of BV and wind increases, the inertia of the system becomes lower and lower. And if this is lower and lower, in this case, the oscillation here of the speed and the frequency in turn becomes higher and higher. But this is the challenge of high penetration of the renewable energy here. So there are some countermeasures, some of the international experience from different countries. They are trying to increase the inertia by what we call the virtual inertia. This is some kind of bar electronic devices also to behave as synchronous generator. This is one way. The other way, in some places in worldwide, in Australia specifically speaking, they they maintain the synchronous generators and all the synchronous generators, and they run them as synchronous motors. If we have also synchronous motors, this will contribute to the inertia of the system. So this is some of the measures. We can have more details later on how to increase the inertia. But in general, Sulaiman, your question is for BV or wind. Since we have bar electronic interface, it kills the inertia. Generally speaking, I'm calling in general speaking, without going in details of the wind. You have several types of wind turbines, all fixed speed, connected to the through the complete interface with the bar electronics, or doubly fed induction generator, or you have some kind of synchronous permanent magnetic. Without going in details of the wind types, you have if you connect the BV or wind, the inertia will getting lower, and you have high frequency oscillation here. So, and this is limits the penetration of the renewable energy. I hope I address your question.
Yes, Dr.
Okay. So this equation can be written in terms of first order. Instead of having second order differential equations, instead of having the second order differential equation, we can express it in terms of first order differential equations. In this case, we have two first order differential equations, d omega by dt, which is the acceleration, same equation, but this is the acceleration, and d omega by dt, or d delta by dt, equal to omega minus omega synchronous. Omega synchronous اللي هي constant 2 by f, or 2 by f0 synchronous, and this is equal to here in Saudi Arabia with 60 hertz, 377 radian per second. So this is d delta by dt. Omega m per unit, if you express it in per unit, this omega s will be 1. And omega s equal to this in radian per second. And this is equal to 1 in per unit. Okay, so omega s, if you express it in radian per second, by 377 for 60 hertz system. If you express it in per unit, in this case you have 1 per unit here. So this is the swing equation, or you can have it as the 2 first order differential equations. Comments on the swing equation. The plot of delta versus time, and okay, the solution of this swing equation is simply having a delta of t. You need to draw what we call the swing curve. This is delta 0, and then we have any disturbance, any load changing, and so on. So you have this kind of response. So this is delta of t versus t here. So this is the solution of the swing equation. So the plot of delta versus time yields the swing curve. The stability of a power system can be determined from the plot of the swing curves of all machines in the system. And if you plot all the angles of the generators that you have in your system, you can find like similar. This machine has delta 0, 1, and this is the response. The other machine has this angle at the beginning, and this is the response. Other machine, you have it here, other machine, and so on. Maybe one machine will go unstable, and you have to isolate it somewhere here. This is unstable. But some machines you can go back to its original place. So drawing this delta of t versus t for all machine, you can check whether your system is stable or not. So you have to solve the swing equation. The mechanical input Bm in the swing equation is considered constant. Usually in solving the swing equation, we consider Bm as constant. Bm equal to constant. Why? Why is that? Why is that? Any answer? Why we consider B mechanical equal to 0 in the swing equation?
Yes, Doctor.
Yes, please.
Because it's slow compared to the power, electrical power.
Again, please.
It's very slow compared to electrical power.
Yes, you are right. Okay. Mechanical power. So you need to, in order to change the mechanical power, as we mentioned earlier, in order to change the mechanical power, you need to control the steam going to the turbine. And this is done through the governor. You have your boiler. So you have your boiler, and this is the case. So this mechanical system is very slow compared to the time frame that we are seeking for the stability of the system. So we are writing here, as we mentioned in first, when we talk about the time frame of the power system studies, in transient stability, we are interested in few cycles after the disturbance. A few cycles means in millisecond, يعني 100 millisecond مثلا, or 1 second. Up to 5 seconds we can. Up to 5 seconds, this mechanical system is not responding. The time constant is high. So this is a good assumption to have B mechanical equal to constant in this study. Okay, so can be expected to change before the control governor code the turbine to react. Okay. So again, if BA equal to 0, BE equal to B mechanical, the machine operates at the steady state. If BE changes in BE could result from severe load change, any disturbance, faults, load changing, switching of some lines or so, and so on. So the solution of the swing equation is very difficult. Why it is very difficult? Why is very difficult? Swing equation here. Why it is very difficult? Can anybody tell us? Please raise your hand in order, but just to make things in order. So if you have an answer, raise your hand. Omar.
Yes, because it's non-linear.
Non-linear. Why non-linear? Where is the non-linearity here?
Yeah, the term on the left hand, I mean, 2h divided by.
Here is the nonlinearity. Nonlinearity is embedded in calculation of B electrical.
Okay.
The form of B electrical, as you know, is V1 V2 over X is sine delta. So if you could express BE as a sine delta here, then it becomes nonlinear equation. It's very difficult to solve. So you need to solve it either by numerical integration or by graphical solution. The solution of the swing equation is very difficult, even in case of single machine infinite bus. Single machine infinite bus. You have only one machine, and the equation becomes difficult. What about if you have multi-machine system? Such difficulties arise of the nonlinear nature of the equations, or specifically the electrical power. In stability studies with many synchronous machines, and if you have multi-machine system, only 1 megavolt ampere base common to all parts of the system can be chosen. This is usually the case. When you have a per unit system, you are considering only 1 megavolt ampere, like 100 megavolt ampere base. And of course, you adjust all the quantities according to the new basis you consider. So also here, we have the same. And you have H, when we define H, we define H compared to the S machine. And if you have different machine in your system, in this case, this H is related to that specific machine. So if you have different machines, in this case, you have to modify this H. As we mentioned, then H is some kind of per unit quantity and related to the base of the machine itself. But if you have an overall system, in this case, you have to modify this H with respect to the whole system, not to this specific machine. So in this case, since the right-hand side of the swing equation must be expressed in per unit for this common base of 100 megavolt ampere, H also must be the same. H of each machine must be consistent with the system base. And you have to modify also H here. This can be done by multiplying both sides of the swing machine by the ratio as such, and you end up with this formula, similar to what we have in resistance and reactance per unit. If you want to change the basis and to do this or that, so this is the case. And H with respect to the system equal to the H given with respect to the machine multiplied by S machine over S system. So when you have multi-machine system, you have to keep this into consideration. And this is very important. You have to modify the inertia constants for the whole system. If it is single machine, infinite bus, خلاص, it's okay. And a single machine, infinite bus, no problem. But if you have a multi-machine with different sizes, with different megavolt ampere, you have to unify your megavolt ampere base. Okay, so now we will see how to calculate this B electrical. The B mechanical, we will consider it constant. So what about B electrical? B electrical, we will see the cylindrical rotor synchronous generator. This is the first one. Second is salient pole, as we mentioned earlier. When we have here a regular air gap, here the air gap is irregular. Okay, this is discussed earlier. So for cylindrical rotor, you have E, and this is the impedance, and this is the voltage, the load, and so on. This is the equivalent circuit of the synchronous generator, and of course this is the phasor diagram. This is the phasor diagram. This is the current. This is the voltage. Let us take this voltage as our base, our reference, with angle 0. So this is the armature current, and this is IARA, and this is IAXS, and this is IAZS. So this is the internal voltage E here. The power between E and V is called the delta. The power between I and V is called here theta. What is delta? What is this? And what is this? What is this angle? What is this angle? This is what? Delta. Ayub?
Theta, I mean, it's cosine theta to give us the power factor.
Theta, يعني theta is a phase angle. خلينا نقول theta is a phase angle between voltage and current. Cosine theta to the power
factor.
And the power can be expressed as VI cosine
theta.
Okay. So what about delta? Omar?
Load angle.
Rotor angle, right?
Yes.
Or power angle, as we mentioned earlier. And this delta we can find also be equal to EV, the internal voltage, over times the external voltage here, the first V1, V2, E times delta, over X S we sine delta. طبعا in this we assume in the resistance equal to 0. If we don't have a resistance equal to 0, we will derive the equation now. طبعا you have a little bit different than this formula, but if RA equal to 0, the power transfer here between any 2 points equal to the voltage here times the voltage here over the reactance sine the angle difference. If this is angle 0 and this is angle delta, so sine delta. So the power of the machine can be expressed as such or can be expressed as such. This is the rotor angle, and this is the phase angle. Abu Bakr Hassan, do you have any question, Abu Bakr?
Doctor, I asked for the physical meaning of the rotor angle.
Physical meaning of the rotor angle?
Yes.
Well, okay. Here, you know the synchronous machine and what is the rotor of the synchronous machine? Rotor, assume that we have salient ball, and to things to be clear. Yani. So this is the salient ball. You have here north ball, and you have here the stator. Okay, is it clear? Is it clear?
Yes, yes.
So here you have winding, and these windings you have like north poles, south poles, and so on here. So the this rotor, assume that this is let us express it in terms of, or describe it in terms of the motor to be more clarified. So if you have here synchronous flux here is rotating by synchronous speed. Okay, when you have a load on this rotor, what will happen for this rotor? And if this is the reference for the stator, if you have no load, if the machine is running light, no load, also the rotor will be in the same. There is no phase, or there is no shift between the flux and the stator and the flux and the rotor. But if you start loading this rotor, and I'm talking about motor just to clarify it. If you start loading this rotor, what will happen for this rotor? What will happen here for the rotor? The rotor will start, comes the lag of the synchronous flux here, which is rotating at synchronous speed. So the rotor will start delaying here with this angle. This is delta. This angle is called delta. You have two flux in stator, flux and rotor, and they are running in synchronous speed if there is no load. But if you start loading, in this case, you have delta shift here. If you increase the load on the rotor here, if you increase the load on the rotor, what will happen for this delta?
Will increase.
It will increase. And again, it will increase. Until what is the stability here? Stability limit. This is the stability limit. 90 degrees. بعد 90 degrees يحصل what we call the bull slipping. Bull slipping. لأن in this case يعني هنا النورث والساوث لو أكثر من 90 degrees, now we have some kind of north with north. Right? Is it clear?
Yes.
So the angle here is the rotor angle or bar angle, which the angle between the rotor and the stator, the flux of the rotor and the flux in the stator. So this is the rotor angle, or this is the bar angle. You know, bar, as we mentioned, the bar is a function of this delta. I hope this clarifies the point.
Yes.
Okay. So the machine sine or the output power here equal to VI conjugate, and the armature current equal to E times with angle delta minus V over the impedance with angle gamma. طبعا if we have RA, then this gamma is below 90 degrees. If we have only XS, so this becomes GXS or 90 degrees. So if we have a resistance here, what would be the power? So of course you can take the derivative, the conjugate of both sides. So S conjugate equal to V conjugate, which is also V times I. If you expand this to E cosine delta plus J E sine delta minus V with angle 0, and this is equal to RA plus GXS. You multiply by conjugate and you do some kind of manipulation. So at the end, you will end up with this formula. So this is the power calculation. It's equal to B plus JQ. Okay, so if you have EV ZS cosine plus J sine, cosine plus J sine, you combine the imaginary parts as Q and the real parts as B. So you can have this B now is equal to this. We just expand this equation to cosine and this term also to cosine. So cosine, the real parts. So this is the electrical power. EV over ZS. طبعا ZS here equal to square root of R square plus X square. This is the magnitude now. E magnitude of E, magnitude of voltage, magnitude of impedance, cosine gamma minus delta. This gamma is impedance, the angle of impedance, which is approximately 90 degrees. If we neglect the R, if we neglect the RA, if RA is 0, then gamma equal to 90. And the cosine 90 minus delta, and the cosine 90 minus delta equal to sine delta. So we end up with that term. And the cosine 90 equal to 0. So this term will diminish. And you have EV over X, resistance equal to 0 here, you have EV over X, sine delta, which is the original equation that we start with. Okay, QE, which is the imaginary parts, if needed, RA is neglected, then ZS equal to JXS and the gamma equal to 90 degrees, and then you can reduce B electrical as such, and also the maximum power here is EV over XS. So you can express also Q as if 90, if this is 90, that will be cosine delta, and if this 90, it becomes 1, sine 90 equal to 1, so it becomes V square over XS. Is it clear? Abu Bakr Hassan, do you have a question?
I don't have a question, Doctor.
Okay, your hand was raised and you probably forget it. Okay, so salient pole, where you have here two or irregular air gap. So you have here the rotor of north-south poles. You have two poles here actually for this structure. And this is the rotor winding or field winding here. This is the field winding. And you have here the stator is three-phase winding. Three-phase winding, you have phase A and the end of phase A, 180 degrees. And phase B which is 120 from phase A, and this is end of B. And this is C, which is 120 between B and A, and then this is the end of phase C. So this is the armature winding. Okay. Usually the field axis, this is the field winding. So we consider the rotor axis here as a direct axis. The field is an direct axis. Okay. طيب, we call it direct axis, and the other, which is 90 degrees, is called the quadrature axis. So this is the direct axis of the machine, and this is the quadrature axis of the machine. What is the angle between D and the Q axis? Here. What is the angle?
90.
90 degrees.
$90 degrees. Mechanical ولا electrical?
Mechanical.
Mechanical. طيب, electrical. كم الانجل between Q and the D axis?
Same 90 also.
Why?
One pair ball.
Exactly, yes, you are right. Here, since we have 2 balls only, so number of pair of balls equal to 1. يبقى theta mechanical equal to theta electrical. So the Q axis and D axis, the angle is 90 degrees. But if we have 4 balls, this is the D axis. Where is the Q axis? If this is the Q axis for the machine, or what?
Mechanical or electrical?
لا, الكيو اكس اللي هو الميكانيكال electrical. So this is the Q axis of the machine. This is the Q axis. Is it clear or not? 90 degrees. Here, this angle is 90 degrees electrical. Am I right?
Yeah, but is it always 90 degrees? That's a constant thing between D and Q?
Yes. Between D axis and the Q axis, 90 degrees electrical. Okay? So here, this angle is 45 mechanical. Then the number of pair of balls equal to 2. So we have this equal to theta mechanical times the number of pair of balls to get a theta electrical. So we have here 2 pair of balls. So theta mechanical here is 45 degrees. And this is, if you look at the sinusoidal waveform, you have here, this is sinusoidal waveform. When this ball, assume that this is the ball here at the beginning, or here, it doesn't matter. If the ball, if this is the ball here, this ball is rotating. So when a conductor here comes under this ball, mechanically you have 90 degrees, mechanically. But this is south pole, and you are where you are here. So you have here 180 degrees electrical, while 90 degrees mechanical only. Is it clear? Is it
Yes,
clear?
doctor. Yes.
Okay. So the angle here is the direct axis. Since we have, this is a special case, and we have here only 2 poles. So the direct axis and the quadrature axis, which is 90 degrees electrical, it is the same also mechanical here. But anyway, so this is the D axis and the Q axis. This is the field winding, and these are the air gap, and the air gap here is irregular. So we have here, this is the air gap at this part. You can see this length, LG. But here under the pool, you have, this is LG, which is very small here under, but this is very long. So you have a regular air gap. So in this case, you have what we call XD and XQ. You have reactance in the direct, and you have also another reactance in quadrature. Then in quadrature, if this is the quadrature, the air gap here is long. So what do you think? If the air gap is long, with longer air gap, what do you think about the reactance? Is it greater or lower? And I mean, and if the air gap LG increases, how much X increases or decreases? If you have increasing air gap, what about, okay, Ramadan Ali?
Doctor, I have a question about QX, mechanical QX. Is it always 90 degree fixed or it's changing?
Which one?
Q axis, the mechanical Q axis.
Q axis in our work is electrical. We are looking at the electrical axis now. It's not mechanical axis. And when we say D axis and the quadrature axis, we may have, as we mentioned here, mechanically, this Q axis mechanically is 45 degrees from the D axis. Mechanically,
okay.
But electrically 90 degrees fixed. Electrically, the angle between Q axis and the D axis is 90 degrees.
Always.
Fixed. Always.
Okay.
But not mechanical. 90 degrees electrical. 90 degrees electrical, which may be different than the mechanical angle. And if you have more, if you have, for example, 6 poles. If you have 6 poles, the number of their poles equal to what? Equal to 3. So 90 degree electrical equal to theta mechanical multiplied by 3. So theta mechanical equal to 30 degrees in this case. And this is between QX and DX. If this is DX, but this is the QX. This is 30 degrees mechanical, but 90 degrees electrical for this sinusoidal waveform. The voltage of this, of a conductor here, will be 90 degrees in between if the pole is moving only 30 degrees mechanical. Is it clear?
Yes, clear. Thank you.
Okay, Abdulaziz, Khalid, do you have a question?
Yes.
Or do you have an answer? And I think we.
I have a question and an answer.
Okay, go ahead. طيب ما تخليها خلاص يعني self contained وخلاص.
No, I would prefer to ask a question.
Yeah, I'm kidding يعني أنا عارف يعني هو الانسر ممكن ما تكونش خاصه بالكويشن اللي عندك يعني anyway.
Okay. Dr. D-axis and Q-axis, I've noticed that they are being used even in modeling the machine. So, okay, I see it now. But why do we have them? What's the purpose of having
This is a good
D-axis?
This is a good question. احنا there is you know here we have 3 phases. And the phase shift between A and B are 120 degrees and C also 120 degrees and so on. So currents, voltages, they are with 120 degrees phase shift and so on. Here, for synchronous machine, we need to convert from the 3 phase of 120 degrees phase shift, which is complex in analysis, to only 2 phases or 2 axes only, direct and the quadrature axis, with 90 degrees in between. So the analysis becomes very simple. Later, we will explain this called Barks transformation, which convert from ABC to DQ. And any current, any voltage in ABC, you can convert them to D and Q components. IQ, ID, VD, VQ, and so on. So the analysis here becomes very simple. Then the direct axis and the Q axis is 90 degrees, and you can work on complex numbers. Okay, ID plus GIQ. So the current here ID plus JIQ, and you can add whatever. So you convert from 3 phase quantities, which is the phase shift is 120 degrees, to just real and imaginary or complex number. So this is called the Barks transformation. We will discuss it later on. Okay. So usually in analysis of the machine, we convert the 3 phase to D and the QX. So this is the question. What about the answer?
For if the length increases, I believe the inductance will increase.
Oh yeah, this is the question here. If LG increases, what about X reactance?
I believe it should increase also.
It should increase. طيب, any other answer? Ramadan Ali, you still raising your hand?
By mistake, Dr. Sorry.
Okay. طيب, let me ask you one question. If LG increases, what about the reluctance? Reluctance, اللي هي magnetic resistance. What about the reluctance? Increases or decreases?
I believe it increases, Doctor.
Yes, it increases. Reluctance equal to, you still remember, and the reluctance equal to L over mu A. L طبعا L in general هو length of the magnetic path over the permeability of the material, the iron core and so on, over times the cross-section area. Okay. طبعا if you have an air gap, so it becomes L plus Lg. Usually L of the magnetic of the iron core can be طبعا it's long, but the permeability is very high of the iron core. وبالتالي يعني mainly the governing equation is the reluctance of the air gap. So if you increase the air gap length, if you have here increasing air gap length, the reluctance will increase, but the reactance will go low. لأن الإندكتنس reluctance and the inductance equal to N square over R, where N is the number of turns, number of coil turns. So inductance is inversely proportional to the reluctance. So if reluctance increases, then X will decrease. So you have here different values of XD and XQ. So in this case, it becomes very crowded now. Let me. Do you still see it clearly or not clearly? Huh? The figure now.
It's clear.
Let me just do it here. Let us. Okay, we have it here. And the other, okay, خلاص, let us continue. We have it is in the other slide. Okay. So in this case, definitely XD not equal to XQ, which is the difference between cylindrical and salient wall. In cylindrical, the air gap is regular air gap, so LG is constant, وبالتالي XD equal to XQ in cylindrical. Whatever here in the salient, we have different values, XD and XQ. So this is the phasor diagram of the machine now. You have the current IA, and this current IA has two components, one in the direct axis and one in the quadrature axis. This is the direct axis, and this is the quadrature axis, ID and IQ. And also V, you can have it VD and VQ. E, what about E? Do you have ED and EQ? Well, E is in QX only. What do you think? While E here is in Q axis. There is no component of E in direct axis. What do you think? Why? This E, sometimes you call it EQ in quadrature axis. If you know the Faraday's law, if you go back to the basics, in Faraday's law, E equal to N d phi by dt. And this if phi, if it is sinusoidal, so this E would becomes cosinusoidal. So you have phase shift between the voltage and the current, between the flux and the voltage, and the induced voltage by 90 degrees. So if we have the flux in direct axis, and this is what we conventionally use, the direct axis, the direct of the flux. If the flux in the direct axis, well, induced voltage will be in the quadrature axis. So this is EQ or E, and this is the voltage. Of course, if you move through the voltage, you have it here, two components, one in direct and one in quadrature. This quadrature is perpendicular to the IQ, and this one also is perpendicular to ID. This is ID XD, and this is XQ IQ. So you can have it here. This is E. So this theta, still we define theta as a phase angle. Delta is the rotor angle or power angle. And definitely, if you have what we want to do here is to, as we did in the cylindrical, we derive the equation of B electrical. What we want to do here is to derive the equation of the B electrical. B electrical here will be expressed in terms of VDID and VQIQ. So how can we get this VD and VQ here? Is it clear what is the objective? Ayub, Wael?
Excuse me, Doctor.
Yes.
Doctor, you know, the D and the Q axis are rotating, right?
Yes.
Oh, okay. That's why you are saying, you know, if the E, it's EQ because, you know, the flux in the axis always.
Yes. Yes.
Okay. Okay.
Flux in the axis. This is the north pole, and the flux is going this way. Okay, this is the flux. So this is the direct axis. This is the axis of the flux. So the induced voltage will be in QX. Okay. So what we have here, we need to express the voltage and the E and the current all in the DX and the QX. And we can say, you know, power equal to V times I cosine theta. So you can express E as V, you have here, this part is V cosine delta. And up to here, this is V cosine delta plus XDIQ. So this is the E. And VE equal to VI cosine. Can we express V in terms of VDID, VQIQ, and so on? And then we can substitute in this equation to get the electrical power of the salient pole machine. Okay, let us IA cosine theta. Of course, we can have this perpendicular here in order to express this in terms of the angles. So IQ or IA cosine theta, I have this angle here is 90 also, 90 degrees, and this angle is 90 degrees. This is parallel to this one, so parallel to this one, which is V. You can have this 90 degrees, and this is also 90 degrees. Okay. So IA cosine theta. Where is IA cosine theta? This is IA cosine theta. This is the IA cosine theta gives you this part from A to C. It gives you the value from A to C, which can be considered as AB plus BC. And the BC is the same as DE. And this is BC or DE. AB, this is AB, which is IQ cosine delta. IQ cosine delta. And DE or BC, which is ID sine delta. If this is angle delta, this is also angle delta. And if this is ID, if this part is ID, so this one is ID sine delta. So this is IA cosine theta. This is IA cosine theta. Okay. Substituting, well, V equal to V times this. And from the phasor diagram, V sine delta equal to XQIQ. This is V sine delta. And IQ equal to, you can replace the IQ by V sine delta over XQ. Similarly, you can have from the first equation, you can have ID equal to, where is it? ID equal to this, E minus V cosine over this. Substituting in from ID, IQ, you can have the electrical power expressed in E and V. So this is EV over XD sine delta plus V square XD minus XQ over this sine 2 delta. So you have here sinusoidal waveform with double frequency here. And this is the electrical power of the salient bone. Of course, if you have cylindrical rotor where XD equal to XQ, but this part will diminish and you have the original one here. And this part comes from the saliency effect. Is it clear? I think the time is over, and also we finish this part. Do you have any question? Do you have any question?
Doctor?
Yes, please.
About PE, electrical power. If we have contribution from conventional power and renewables, do we consider renewable to be part of PE?
BE. Where in you want to consider the generation from the PV or wind as a part of electrical power?
Yes. Do we consider it?
لا انت you consider انك انت you have some kind of constant generation from PV, right? So you can they are constant. طبعا احنا we will not consider the dynamics of this, but if you have constant generation, so in this case your load you just add it as minus BG in your load. Is it clear?
Okay, clear. Thank you.
Ramadan Ali?
Yes, clear, Doctor. Thank you.
Okay. So if you don't have questions, so you can leave. If you have questions, you can stay. Hussein Ali?
Yes, Doctor. Assalamu alaikum.
Salam.
Actually, I don't have a question, but I have a suggestion. If we could start a bit earlier, 20 minutes, for example, at 5 o'clock, and we may have a break during the lecture to pray the Maghrib prayer, since today 5:20 they just call for Salah.
Yes. So, Shabab, what is your opinion? And if we agree on something, we have to stick with it. So, what do you think?
Yes, Doctor, I think it's okay. I think I am in support of this.